This is strain gauge method. So I showed you in this morning, it's a all type strain gauge system, but it's currently we use this type of system. It's the concept is similar, but there is a blade here, and this is a support. And at the hub portion of each blade, we put the strain gauge on the blade. And if this is inserted in the wind tunnel flow, there is a small deformation of this part of the blade. So we can detect the deformation of this, the root part of the blade. And from this signal of deformation, we can calculate the aerodynamic force working on this blade, the whole blade. And of course, we need calibration. This is calibration. And this weight, we put weight on this blade. And we can detect the signal of strain gauge. And then we can calibrate this strain gauge signal. Okay? And this is a strain gauge method. And we use also oil flow. As I showed you, we can visualize the flow on the blade surface with an oil flow technique like this. And we also use this oil flow technique to the wind tunnel flow. So this is a wall of the wind tunnel. And we visualize the oil with the oil flow technique, the flow on the wall surface to make a good flow of the wind tunnel. And this chart shows the Schlieren technique. So it's an optical technique to detect the shock wave and also the wake or boundary layer. So it's the light path is shown here. From light source, we use this, like it's a half mirror through half mirror, and it's a concave mirror. But we can get the parallel light here, and it's entered into the flow path. And this is a wind tunnel wall, and this wall is glass window, so it's transparent. And the other side, we use the mirror disk here. So we can catch the reflected light here, and then concave mirror and half mirror, and we can detect the both this source light and reflected light. Both of them can be caught in the high-speed camera, and there is a knife edge. So because if there is a steep gradient of density in the flow field, the refraction ratio changes. So the path of the light is changed by the diffraction index change. So if we cut that reflected light by knife edge, we can detect the region of the steep density gradient as a dark part. So that is a Schlieren technique. Okay. And then, as I told you, we need to have very good uniformity of the flow field in the cascade. But it's a very difficult task in this linear cascade tunnel. So we are carefully arrange the configuration of the blades or the walls. And this is the current flow field results. So the abscissa is blade number 0, 1, 2, 3, and -1, -2, -3. And it's a static pressure ratio. Oh, no. We measured the wall pressures, the one called downstream region and also one called upstream region. So it's from here, so this is very flat. The the distribution is very flat. But here, it's not good. So minus 2, 3 is here, upper blades. So this is a static pressure ratio between upstream and downstream. So we need to have a flat distribution. But minus 2, minus 3 is not good. But we can get the uniformity from minus 1 to 3. So we use only these 3 blades, 3 channels for the experiment. But hopefully we need to get a more flat distribution here also. And we also did some CFD calculation on the cascade tunnel, wind tunnel flow, okay, and to check the flow uniformity or flow property in the basic flow in the wind tunnel. And we are using the in-house code. It's a governing equation to 3D runs and Schass technique, and turbulence model is K omega Wilcox model. It's a very standard approach to the CFD analysis. And the grid is shown here. We have it's not for only wind tunnel flow, but also for flatter case. So we have a non-reflection boundary condition here. This is an inflow boundary, and this is an outflow boundary. And we use periodic boundary condition here. Okay. And it's a 3D case, but this is a moving grid technique. Okay. And we use the overset grid method for wind tunnel simulation because it's a very complicated configuration. So not only the blades, but walls here. And also whole view is computational grid for wind tunnel. And there is very complicated structure. It's, for instance, test section is, the grid for test section is like this. And there is an throttle valve here, so valve is here. And there is a porous wall for making the uniform flow. We are using porous wall here. So porous flow is also modeled by the grids. So very complicated, but it's a zonal method. And we calculated the flow field in the whole wind tunnel. And this is an experiment. It's a hub sidewall and tip sidewall can be visualized by oil flow technique. And this is a 2-dimensional simulation. And we found the weak shock wave is generated here. It's an upstream region, or full span shock wave in the wind tunnel. And this is we measured this is a blade number, and it's we measured the pressure, as I told you. It's a symbol, the experimental result, and line is a CFD result, so they have very good coincidence with each other. And then the shock wave in the upstream region. So this is an nozzle position against isentric Mach number, or we measure the pressure on the wall, and we can calculate the isentropic Mach number by the wall pressure data. So it's plotted like this, and and CFD results is line, and the experimental data is symbols, and blue symbol is the data on without suction, wall suction. So we need the wall suction anyway, but if we use the wall boundary layer suction, it's much better. Okay, and it's a very good agreement with the CFD results like this. And in the visualized view, we can find the shock wave here, like this. But fortunately, the shock is not so strong, so it's the flow inflow to the cascade is still supersonic. But we have to correct the Mach number. We thought it should be 1.2, but in reality, the correct Mach number is 1.17. So we used this value as an inflow Mach number, inlet Mach number. And the flow field in test section, it's CFD results. And we can clearly detect the density gradient like here. And we can have uniformity, at least these 3 blades in the middle point. But we can find some flows the outside of the test section like this. And we compared it with the visualized view of the by the oil flow. So this similar flow field is obtained by the CFD simulation. So this is an effort to get a good flow field in the wind tunnel. But nowadays we can use this kind of CFD. So we can use both CFD and experimental data and combine them to get a very good flow field inside the wind tunnel. Okay. And this is a visualized view of the by the Schlieren technique. So we can use the horizontal knife edge and vertical knife edge. It means horizontal knife edge or vertical knife edge. So it's the visualized view is different. So if we put the horizontal knife edge in this experiment, the flow direction information can be detected. So for instance, the inlet flow, blade wake, or blade surface separation. But if we put the knife edge vertically, we can detect the vertical direction information. For instance, blade leading edge oblique shock and passage shock on the expansion wave. So in this experiment, we are focusing on the behavior of the shock wave. So we are using the vertical knife edge. And so pressure ratio is 1.25, that is here. So the double shock wave, the oblique shock and passage shock pattern is realized here. But near detached shock wave here, so one oblique and normal shock pattern is merged. And so this is not so stable. It's near detached. And if it's really detached, it's very unstable situation occurs. Okay, so maybe this is maybe we can, yes, this is. So this is a steady state experiment, but as you can see, there is some oscillation, inherent oscillation in the flow field, steady flow field. Okay, so that is very important to think about the unsteadiness, inherent unsteadiness of the flow field before the flutter test. Okay. Okay. Yes, here. Yeah, if the pressure ratio is 1.25, we have oblique shock wave here and passage shock here. So we call it a double shock pattern. And here it's a higher back pressure, higher pressure ratio. The oblique shock and normal shock merges each other. So it's one shock pattern. Okay. Okay. So this is an additional information concerning the experimental technique. And then I'd like to discuss several points written on the sheet. So please consider the answers of these questions. 10 word 20 minutes, 15 or 20 minutes, and then I'd like to discuss the contents.